Did you know? The transformers we use today aren't necessarily those big, heavy hunks of iron wrapped in copper wire anymore. In the world of power engineering, a new player has entered the game: the solid-state transformer. And let's be clear, this isn't just a miniaturized version of the old tech, and it's definitely not just a marketing gimmick. This is a revolutionary power conversion technology that is quietly renewable energy systems, and even how we charge electric vehicles. Many people think an SST is just an electronic version of a standard transformer. But in reality, its principles, architectural efficiency, and capabilities are an entire generation ahead. 1. Why develop solid-state transformers? To understand the SST, we first have to ask, why aren't traditional transformers good enough anymore? Think about it. The world of electricity today is completely different from 50 years ago. Back then, the grid was a simple one-way street. Power plant gives transformer, gives distribution, gives consumer. But now we have solar panels, wind turbines, EVs, energy storage batteries, microgrids. Electricity does not go out, it also flows back. This makes the old transformer architecture look clumsy and unable to cope. Traditional transformers are strictly for unidirectional transportation. They are like a single-lane road. They can deliver power, but they can easily accept it back. Plus, they have no brain. They can see the current status and they can tactically adjust. VOLTAGE, or power factor. In this era of the smart grid, we don't just need the muscle to move electricity. We need a central nervous system that can think, control, and communicate. That represents the reason for the SSTs. It combines power electronics, communication control, and digital computing to become a smart node for the future grid. 2. The traditional transformers, the heavyweight champion. The transformer we are all familiar with works on a very pure principle: electromagnetic induction. Current flows into the primary coil creates magnetic flux induces voltages in the secondary coil. The voltage ratio is simply decided by the number of turns in the coils. This design is stable, reliable, and can handle massive power, which is why it's used everywhere, from substations to factories. But it has some glaring limitations. It's bulky and heavy. It's stuck at fixed frequency. It can tactically regulate output voltages or power factor. It has almost zero intelligence. In other words, it knows how to move electricity, but it doesn't know how to move it smartly. The solid-state transformer, the smart athlete. The key to the SST lies in the words solid state. This means we are replacing magnetic field conversion with semiconductor switching components. Its internal structure is actually a three-stage power converter. AC-DC, it rectifies the incoming AC into DC. DC-DC, it uses high-frequency switches and an isolation transformer to change voltage. DC-RC, finally, it inverts it back to a C output. This design gives it capabilities that traditional transformers can only dream of. Compact and lightweight, smart control over voltage and power factor, bi-directional energy flow, real-time communication with the smart grid. If the traditional transformer is a pure muscle mover, the SST is a power manager with a II intelligence. 4. Practical differences. If I had to describe the difference, imagine the traditional transformer as an old-school tough guy, while the SST is a high IQ athlete. First frequency. Traditional ones work at 50 or 60 Hz. SSTs operate at tens of kilohertz. High frequency means the magnetic components can be drastically smaller and more efficient. Second, size and weight. For the same capacity, a traditional unit might weigh tons, and SST might weigh just a fraction of that. Third, efficiency. Traditional is around 95%. TS can reach 98% or higher, especially significant in medium voltage distribution where energy loss matters. Fourth, control. Traditional is passive. What goes in comes out. SST is active. It detects, analyzes, and corrects voltage, waveforms, and power factor on the fly. Fifth, energy flow. Traditional is usually one way. SST is bi-directional. It can send solar power to the grid during the day and charge batteries from the grid at night. Sixth, applications. Traditional is for factories and transmission lines. SST is designed for EV fast charging stations, solar farms, wind power, microgrids, and even aerospace and military systems. 5. The advantages. So why invest money and time developing such a complex thing? Because the SST offers 5 massive advantages. High frequency miniaturization. Higher frequency means higher magnetic flux density, shrinking the volume by 10 times for the same power. High efficiency. Using SiC and GaN components reduces conduction loss, pushing efficiency past 98%. Smart control and MIPS in built-in microprocessors allow for real-time monitoring and control. Grid support. It can balance loads, recover energy, and stabilize voltages. Modular and scalable. You can stack SSTs like Lego blocks to increase power or build microgrid nodes. These features make it an indispensable core component of the smart grid. 6. Challenges and future trends. However, every technology comes at a price. The biggest challenges for SSTs, right now, are cost and reliability. First, power semiconductors are still expensive. Second, heat dissipation is a bottleneck. High frequency switching concentrates heat, requiring precise thermal design. Third, repair is difficult. You can just change the oil or a coil like in the old days. The SST is full of chips and circuit boards. But the good news is, these issues are being solved fast. As material cost drop and integration improves, SSTs are gradually entering the medium voltage distribution field. Major research bodies like the US DOE and the EU's Horizon program view the SST as the intelligent hub of the future grid. Crucially, in EV charging and renewable energy storage, the SST enables instant conversion and bi-directional flow, something traditional systems simply cannot do. Simply put, the SST is the bridge to the distributed energy era. 7. Conclusion. So, to wrap it up, the traditional transformer is the old school powerhouse, steady, reliable, and heavy liftings. The solid-state transformer is the smart athlete, lightweight, agile, and strategic. One relies on magnetic fields, the other relies on algorithms. One is famous for stability, the other pursues efficiency and intelligence. As electric vehicles multiplies, renewables become standard, and electricity starts to flow both ways. That electrical box on your street or that charging station you use might just be hiding a solid-state transformer inside, silently supporting our future smart energy world.